pretty wide-ranging YouTube channel that we're going to be starting here, and I'm really glad you've decided to come along and experience it. This particular lesson today is going to start a three-part series on transcranial direct current. And this will be applicable to people, this will be interesting to people who are clinicians who are applying the transcranial direct current. It'll be information for patients so that if you're investigating whether to use the transcranial direct current or not, it'll be interested to you. And it'd be also interesting to people who are just interested in how the science is progressing and what's happened in the area lately. Now, we are involving all kinds of different things that are involving the neuro component, including laser, gut, all kinds of stuff is going to be included in in this channel. So without further ado, let's get going and let's learn about some transcranial direct current. And in this module, we are going to start investigating and looking at the different modalities that we use to stimulate neuroplastic restructuring or neuroplastic change in the clinical setting. So we're going to be going over the theory and the somewhat the application methods of these modalities. We get into much more detail in the application in the graduate diploma clinical application for those of you who are going on to run your own clinics or be clinicians in a clinic. So we need to start our modality training with understanding, so for the direct current modules, we're going to start with an introduction into current and electricity, just for those of you who have potentially forgotten some of your electricity electronics training. And obviously for things like laser, we'll go into the physics of light and things like that, and penetration and at that point in the series. Now today we're going to focus on the transcranial direct current, and so we'll start with an introduction into the production of current and how it flows and how it acts inside human tissue and the brain. Okay, so don't forget, we do have workbooks associated with the modules and additional reading that needs to be done. So I would highly recommend that you complete the workbook questions in detail, as much detail as you can, because they will help you in the testing and examinations that happen at the end of each module. Okay, so let's get into our topic today. So our topic today is the transcranial direct current stimulation. And what is transcranial direct current? It is basically a non-invasive, painless brain stimulation. Now, we use direct current, and we'll talk about what direct current is in a few slides. But we use direct current to stimulate specific parts of the brain. So with the transcranial direct current, we can both stimulate and inhibit. So it now gives us a bit more flexibility in how we can change the way the brain is functioning. So remember, it's a constant direct current, and it's passed through 2 electrodes placed over the head in specific positions, which we call montages, which we'll talk about in a couple lessons from now, about all the different types of montages that we can use with direct current. So the direct current machine is here. So this is the direct current machine. And out of the direct current machine, we have 2 wires. One is an anode, one is a cathode. And it is connected to 2 electrodes that are placed in a specific position on the head. And we usually use some kind of strapping system to hold the electrodes in place. So it's pretty simple. It is a unit which delivers direct current in a specific current flow, so amperage. and it goes to specific parts of the head or the brain, and based on where the anode and the cathode are, we get different effects from that. So that's what our overall transcranial direct current is all about. And now let's look at how we can understand what's actually happening in the head and in the tissues where we're applying the direct current. So the first thing we need to look at is the how is this current generated? How do we actually make the current move, and what is this current that's moving through the brain or through the body? So let's talk, we'll go all the way back to the atomic structure and electrons and protons and neutrons. If you remember back to your high school chemistry and high school physics, electrons are maintained in a cloud-like concept around the core of the atom and the neutrons and the protons. And these electrons are moving or able to move from one area of the molecule to another area of the molecule, even into other atoms and molecules, if we put them under the right conditions. So the first thing we need to look at is, okay, so what are substances that have tightly bound electrons or loosely bound electrons? How do they differ in how easy it is for their electrons to move or create an electrical current? So basically, this is called conductivity. So the more freely the electrons can move, the higher the conductivity in that substance. Okay, the lower movement or harder it is for electrons to move, then there is a lower conductivity inside that substance. Okay, good. Now, so let's talk about now the actual flow of electrons. So basically materials that we talked about have loosely bound or easily moved electrons. Okay, they have great or high conductivity, so we call those good conductors. While substances that have electrons that are tightly bound have low conductivity, we call those insulators because they insulate the flow of electrons. Now the movement of the electrons, okay, through the circuit or through the pathway is called the current. Okay, so we have the flow of electrons going this way, and by definition the current will flow in the opposite direction. So we have flow of electrons moving from B to A, and we have the current moving from A to B. Okay, so just remember that in as we talk about anodes and cathodes and which direction the electrons are moving and which direction the current is moving in the future slides in the lesson. Okay, now remember we talked about just because a substance has electrons that move easily or it will allow them to move easily doesn't mean they actually move. And in the most cases, they won't move too far, or they'll stay relatively located in their probability cloud around the nucleus of the atom, unless we make them move or we encourage them to move. And generally, we do this by applying some kind of force to the electrons. And so basically, the force that we apply to move electrons is called a voltage or a potential difference. So the potential difference is measured in volts, and it just happens to be named after the physicist Volta, who did a lot of work in this area. So basically, we have a circuit, and the circuit has say a battery. So this battery is producing a current, okay, which is now causing the electrons to move in a certain direction. and produce a current flow. Okay, now note also that the electrons move from negative to positive, and the current flows from positive to negative. So let me say that again. Here's our battery. It's supplying a voltage difference. So here we have a positive differential, here we have a negative differential. And that potential difference is causing the electrons to move from the cathode to the anode. And that electron motion is producing a current. The current flows from the positive to the negative, or from the anode to the cathode. Okay, now the electron flow, so this electron flow here is measured in amps, so amperes or amps for short, and it can also be really, really small currents are measured in milliamps, and even smaller currents are measured in microamps. And if these are named after the mathematician or physicist in the 18th to 19th century, André Ampère. Okay, so just to review one more time, we have a potential difference which is applied through some kind of device like a battery, and that device will provide a differential or a potential difference from one side to the other, and that potential difference will encourage electron flow from the negative cathode to the positive anode, and that electron flow will produce a current from the anode to the cathode. Now remember, the amount of electrical movement, or the amount of electron movement, will be dependent upon a few things. One of the things is the conductivity of the material that we're using. So remember the looseness or the ability of those electrons to move, the ease in which they can move, and also the difference, the potential difference, the size of the potential difference. Now we also have to remember that there's another component of this movement, and that's called resistance. So basically, how much current will flow based on a potential difference that's applied will depend upon the resistance that's in the conductor, or resistance that's in the substance that the electrons are moving through. Okay, so remember, there are good conductors and poor conductors. We talked about that. And a good conductor has high conductivity and low resistance. A poor conductor, on the other hand, has low conductivity and high resistance to current flow. So the resistance is inversely related to the conductivity or conductance. We measure resistance in ohms, and that's in honor of the German physicist George Simon Ohm. And we'll look at how all of these things can be related now through a basic law or mathematical formula referred to as Ohm's law. Okay, so the voltage, or the potential difference, can be thought of the force that pushes electric current through the body. Okay, now depending on the amount of resistance, a certain amount of current will flow for any given voltage. If the current, it's the current that determines the physiological effects that we're talking about. So the changes in the neuron functions that are produced by transcranial direct currents, or any of the currents that we put through the brain, are dependent upon the amount of current flow. Now, we need to look at how we can sort of conceptually visualize what's happening inside the body, and we do this through a circuit which we draw. And the circuit includes a resistance, a potential difference supply, and a measurement of the current that flows. And for any particular voltage that's applied across any given resistance, we will get I, which is the current flow, changing. Okay, So let's just go through this again. V is the potential difference of the voltage. I is the current flow, and R is the resistance through that circuit. Okay? So again, this goes back to your physics and electricity classes in high school, basically. But I wanted to review this because sometimes we forget these things because we don't use them a lot. But these kind of circuits, simple circuits like this, are important in understanding what's happening when we apply current through any body part, but especially the brain. Now, the other interesting thing that we need to talk about is that how is conductance happening inside our body or inside our brain. So most metals are basically examples of good conductors. So copper and silver, and these are the things that we use inside wire. You know, the wires that are wiring your household or that's carrying the electricity to your light bulb or even to your computer are usually based on silver or copper wiring inside, and they're covered by an insulator so that you don't get a shock when you touch them. So the insulator is a poor conductor. The wires on the inside are good conductors. And, you know, the examples of poor conductors or good insulators are glass, mica, porcelain, plastics, rubber. Those types of things are good insulators. But now let's get to the another point, which is that inside our brain, okay, the currents that flow are not from electrons. The currents that flow inside our brain are ionic currents. So they're produced by flow of ions instead of flow of electrons. And the electron flow, or the current that we put through the brain, encourages the ions to flow inside our body or inside our brain in a certain way. So for instance, remember we said when we were using direct current, that meant that the current was flowing in one direction, okay? And it was flowing from the electrons were flowing from negative to positive, and the current was flowing from positive to negative, okay? Now, that electron flow induces different ions, because remember, ions, for the most part, are charged. So they have a positive or negative charge, or a predominantly negative charge, or a predominantly positive charge, remembering back to previous lessons. And the most common movement ions inside neurons and inside the brain are calcium, sodium, potassium, and chloride. So these are the types of ions that are going to be moving inside the brain, causing changes in the membrane potential in the neurons that we're aiming at aiming at changing with the transcranial direct current. So very important concept. When we apply the current through the brain, it's not electrons that are moving inside the brain, it's ions that are moving inside the brain. And we'll see later when we're talking about safety issues and things like that, this is a very important distinction in that the ion flow produces very little heat, whereas electron flow can produce a lot more heat, which is one of the things we don't want inside the brain. We don't want the brain heating up because we're putting a current through the brain that's causing electrons to move, and it's heating the brain up. Okay, so that's just one consideration. So remember, the ions that are flowing inside the brain are induced by the potential difference created across the brain, and that potential difference induces ion flow. Okay, excellent. Now let's talk about the different types of current that we can use. So the first type of current is a direct current. So the direct current, remember we said it goes on, okay, and then it stays constant through the whole stimulation. So it is a current moving. It's moving. We either have the current in a positive direction or a negative direction. So if this was negative, the curve would be down here. Okay, but we have this current. The current's flowing, and then you'll notice at the beginning, and at the end we have this ramp. So the flow of the direct current isn't instantaneous. It has to ramp up slowly and ramp down slowly. Now, it's not that slow. It ramps up quite quickly, but you will see a distinctive ramp. And we can change the ramping in the direct current machines so that we can make it sharper or more take longer. So it can take longer, or it can be sharp and take less time. Okay, and the ramp up and ramp down are important because these usually the ramp up is where people can feel the current moving through their skin. So the sharper this ramp is, the more sensation the DC produces in the patient. And sometimes the patients don't like that feeling. Other times, they don't mind it. So we usually will use a ramping speed or a ramping parameter that is relatively fast, but not so fast that it causes sensation or a lot of sensation. And usually this ramp up will be 1 or 2 seconds. And that usually relieves the tingling sensation that people feel for the most part. So the direct current, we ramp it up. It stays exactly constant, or as constant as we can keep it throughout the time of the application, and then it drops off. And the down ramp usually doesn't create too much sensation in the person, so it's usually quite quick. We down ramp. Now there are other types of stimulation. Now the most common type of stimulation is that, or the most common type of current that we know about, is the alternating current. So you'll see here the current goes one way, then another, then one way, then another. So it cycles back and forth. And this cycle per second, okay, is basically the hertz of the current going back and forth. So in North American countries, usually you have 120 volts with 60 hertz alternating current. In other countries like Australia, where I am, we have a 220 volt, 50 volt, or 50 hertz alternating current. So the voltage and the current delivery frequency in the AC is very important. Okay, because if you plugged in a device, say a computer or some kind of electrical machine or device, into a 120 60 hertz outlet, and that's what it was designed for, then that's fine. It will work great because it's now delivering a current that the apparatus inside the machine, the electronical components inside the machine can handle. But if you take the same machine, you plug it into 220 volts, 50 hertz, you now get a different current flowing through the machine, and it will usually heat the elements up to the point where they get destroyed. So it can fry the components inside your computer, for instance, if you plug it into the wrong AC current. Okay, so it's quite important to understand what these different types of currents can do. Now, in most computers, you have a transformer that will transform whatever current you're plugging it into the current that the machine can use. And so that's why on your transformers, you need to be careful to make sure you're using the right one, and so that the internal components of the machine don't get fried by the electron movement being too great through them. Okay. Now we also have another type of current, and this is you'll see this frequently. It's starting to be used more and more in different types of brain stimulation. And this is called random noise stimulation. So this is a random fluctuation of currents. Okay, so you'll see there is no pattern to this current. Some it's up, some it's down, some it's, so it's a random generation of currents. But it's important to know that the currents are fluctuating. They're cycling, they're going up and down. Okay, so that's the graphical illustration of different types of currents. Now, the other thing that I have previously mentioned is most of the ions that move inside the body are potassium and sodium. Sort of, as we learned, that's how the actual potentials are generated in the axons of the neuron system. We also see calcium movement, which cause the release of transmitters for instance, at axon helix, or sorry, at the axon synaptic structures, where one neuron will synapse with another neuron. But calcium is also important as a second messenger, and a lot of other different things inside neurons. So movement of ions can have significant effect on the excitability, or on the excitability level of the neurons, and also on the ability to cause increased activity or inhibition of activity. Now, the other important thing to remember about the current, especially the direct current that we put in the body, whatever current we put in the anode has to come back out in the cathode. So there will be an equivalent movement of ions as dictated by the potential difference that we put through whatever areas of the body. So if we have a electrode on the head and an electrode on the stomach, the ion movement will go from the head to the stomach, or vice versa, depending on which way we have the potential difference set up, or the anode and the cathode set up. But it's an important concept. Whatever current goes in will come out. And if we're using two electrodes, that means equal current will be put in by the anode and come out by the cathode. Okay? Now, there's another component of connecting something and having electrons flow through different substances like your skin. And that is called impedance. So impedance is basically the combined effect of resistance and capacitance. So remember, the resistance is the ability of something to resist electron flow. And now capacitance is a new concept that we haven't really talked about too much, but capacitance is the ability of a substance to store electrons, or to build a capacity to provide a potential difference. And so usually capacitors are composed of two different layers, really. One layer on one side, one layer on the other, is like a bilaminar membrane, very similar to the types of membranes that we have in our nervous system. So capacitance is a bit important when we're talking about moving current through biological tissue. Now, so impedance basically is recognized as the letter Z. So impedance Z equals the square root of resistance squared plus this formula that you see in front of you. Now, when we're using direct current, okay, our frequency of alternating currents is 0. Because remember, we don't have any alternation of current in direct current. So F equals 0. So if we put 0 here, that makes this component 0. And that means that capacitance, impedance, equals the square root of R squared. So basically, it is impedance equals resistance, or a variation of resistance. Now, impedance is important when we're putting an electrode onto a substance like our skin, because we need to have a flow of electrons. We need to have a flow that's great enough to allow our current to be produced that we want to put through. So on the DC machines, and even on the EEG machines that we use, the electrodes, we have to work within a certain impedance range so that we know that we have a conductance that is able to support our ionic flow that we want. Okay? So you'll hear us talk about impedance, and our impedance needs to be between 0 and 10 or 0 and 5, or so. We'll have a range that we use for impedance. And most research articles on EEG or on direct current will specify what that impedance was that they used in the research that they did. So that will allow someone else to repeat that experiment to get the similar ionic movement that they did in their experiment. So just remember that I'm introducing these things. We'll talk about them again when they become important. You don't have to know this equation or memorize this equation or anything. It's just interesting to know that when we bring in a frequency of modulation or an AC current, an alternating current, then this part of the equation comes into play. Okay, when we don't, when we're using DC, F goes to 0. That means this component goes to 0. That means impedance equals the square root of resistance squared. Okay, so that's just some math for you guys that like the mathematics stuff. Okay, so let's just summarize what we talked about. So current refers to the amount of electrons or ions flowing through a tissue per second. Okay, the current is measured in amperes or milliamperes, or usually we refer to it as amps to be short. So 1 milliamp is 1/1000th of an amp. Okay, and usually with the direct current machines, we're working in some degree of milliamps, 1 to 5, for instance, milliamps. So that's 1/1000th of an amp, ranging from 1/1000th to 5/1000ths of an amp. So the amount of electric current that flows through the body is determines the effects of that modality. So it's the amount of current, or the amps that are flowing through the body, that determine the physiological response. Most current-related effects result from heating of tissue or stimulation of muscles and or nerves. Now, remember we talked about ionic movement produces much less heat. If it's almost irrelevant, the amount of heat that it produces, especially in the currents that we're using. Now, stimulation of nerves and muscles, if your current is big enough, if your potential difference produces enough current, it can actually cause your muscles and nerves to go into a state, something like rigor mortis, or they become unable to move. So if you grab two wires, you'll hear of people that were getting shocked by something, but they couldn't let go of it. And that's because that electrical current caused activation of the muscles to contract, and it was outside of the brain's ability to override that, and they're holding on to this electrical current, which is basically burning them and killing them. So that's why if you do come across someone who has had the unfortunate experience to be being electrocuted, don't touch them. Use an object which is a poor conductor, like wood or rubber or something, and knock the wire from their hand, because they're not going to be able to let go. Okay, so that's just a first aid tip if you come across someone who is being electrocuted. Now, when we talk about the interferential currents that we use, they are alternating currents for the most part. Variations of alternating current. So you can actually be shocked by the interferential current if you're not careful in how you're handling it. So this is this education you're getting now about how currents flow and electrons and potential differences will apply to pretty much all the modalities we're going to talk about in the future. Now, this is kind of what I was just talking about you can get electrocuted. Now, the body has a certain inherent resistance to current flow. And basically, most of the body's resistance to current flow, almost 99% of it, in fact, is actually in the skin. So the skin is our greatest protection against current flow, which is good to avoid shocks and things that are happening in the real in our existence in the real world. However, it also presents a problem when we want to induce a current in the brain, and then we have to go through the skin. So we have to overcome the resistance of the skin in order to produce that current inside the brain. Now, so what are some of the things that can change that current flow? And we need to talk about this when we talk about impedance and electrode contacts, which we'll do in the future. But just getting back to how this resistance can be varied on the skin. If you have a calloused, dry hand, you can get up to 100,000 ohms of resistance just because of the thick outer layer of dead cells that are located in that striatum corneum that will not act as a good conductor at all. Okay? However, if they get through that skin resistance, you'll notice that the resistance drops dramatically from 100,000 ohms down to 300 ohms or so. And that means once that current gets through the skin, it's going to travel very easily inside the body. Okay, and that's generally due to the relatively salty ionic composition and the types of tissues that are beneath the skin that allow easy flow of ions and electrons. Now, you can break down the resistance in the skin by having a cut or an abrasion, or putting water on your skin, so having a wet skin. So you know all this from common sense about getting a shock. It's easier to get a shock when you're wet. It's easier to get a shock when you're in the bathtub. In fact, you can die if you're in the bathtub and the AC current piece of equipment or whatever you're using falls into the tub. So the water drastically reduces the resistance through the skin as well as abrasions. And this is something to remember when you're applying electrodes anywhere on the body. And that is, if you apply the electrode over top of an abrasion, the resistance is going to be less over that abrasion. So you're going to have more current flow through that abrasion than through the rest of the electrode. And that you may result in a painful sensation, could result in a burn on the patient. So you need to be very careful when you're applying the electrodes with any equipment that's causing ionic movement through the skin, about remembering what causes a reduction. So sometimes we, in fact, with DC current, we'll wet the electrode to help us reduce the resistance through the skin, so that we can get a good contact on that electrode and have ionic flow through the brain. But we always want to make sure we're not applying electrodes over top of any kind of skin abrasion, cut, that type of thing. Okay? So I think that will bring our this lesson to an end, and we'll move on in the next lesson, and we'll talk about what actually DC does, the direct current does, how it affects the neurons, and then in lesson 3 we'll move on and cover some things about montages, impedance, and we'll do some case studies so you can see what kinds of effects the direct current can have on different types of conditions that we treat with the DC. And with that said, we'll see you in lesson 2. Bye-bye.